Ew, what's up guys? BabyBear4812 here, coming at you one more time. Today, problem number 98, validate binary search tree. Super popular one, particularly it seems with Bloomberg. Bloomberg loves this one, so do Facebook, Asana, Amazon, quite a few others there as well. Popular problem, and I think this one's tricky. It seems trivial, because all you gotta do is just check a tree and say, is it a valid BST or is it not? Unfortunately, easier said than done. So, instructions are pretty clear, as I said, and they are actually kind enough to kind of tell you what the strict definition of a binary search tree is, which is that the left subtree of a node contains only nodes with keys less than the node's key, okay? Right subtree of a node contains only nodes with keys greater than the node's key, okay? Both the left and right subtrees must also be binary search trees. Cool, so what does that mean? If I'm a node, everything to my left must be smaller than me. Everything to my right must be larger than me. And that must hold for all the nodes as well. All the child nodes and grandchild nodes and all the ancestor nodes. Anyways, you get what I'm getting at. A couple of simple examples. 2, 1, 3 here is a valid binary search tree for the reason that the root is 2. The left is 1, which is smaller than the root. The right is 3, which is larger than the root. One thing to notice here as well, and this will play important, a node, a sole node in and of itself with no children, so this one has no children, that is considered a valid binary search tree, okay? That is considered a valid binary search tree. That's going to be important. And same thing with the 3. So not only is this a valid BST because that one left child node is smaller and the right child node is greater, but they themselves are binary search trees. Okay, that's the key here. We look at this one, and we can tell kind of by looking at it. This one seems kosher, but the 4 is smaller than the 5, and that's no good. The 4 itself seems to be a valid, this kind of subtree, this 4, 3, 6. It is definitely a valid BST, but in the context of the whole tree, this is not valid because the 4, the right child is it's smaller than the 5. I will also point out that this 3 as well is smaller than the 5, okay? So that's something we're gonna need to pay attention to. So let me kind of jump in here and show you guys what I'm talking about. If we look at a couple examples, what am I doing? Pens on, nope. So this, valid, okay? This, I'm sorry, my computer's a bit slow. I think I'm rendering actually another, oh, this is bad. I'm rendering another YouTube video right now, so I think that's it's kind of eating away my CPU. It's 2020, I'm on a 2013 computer, so bear with me. This is also valid, like we saw, okay? Where things start to get a bit finicky is, you know, maybe we have 5, and then we had a 4, and then we had maybe the 6 is here, okay? 6 is good. So we're so far so good. Now we get a 3 here. I mean, we get an 8. This is where the problem becomes, in my opinion, not obvious. When I first tried this problem out, what I said was, okay, let me kind of take on this, you know, we have a tree problem here and those are always going to be recursive. And so I put my head in this recursive mindset and basically thought as follows, okay, well, with recursion, sometimes we think to ourselves, I need to take care of my domain and my own problem, and I'm going to push the rest to somebody else. And we keep on pushing and pushing until we hit a terminal condition, right? We said for recursion, there's always 2 necessary things we need to define. One is the terminal condition, so when do we stop recursing? And the second one is what's the actual recursive relationship. So when do I say, okay, let me take a step deeper, let me call myself again and keep going deeper and deeper. Well, kind of an original thought that I kind of had at least, was, you know, and maybe I'll kind of let's ignore these 2 for now. The 5, 4, and the 6, I'd say, okay, well, let me do a quick check and let me say, if my left child is smaller than me and my right child is larger than me, then I'm good. I'm going to let them figure out whether or not they're BSTs. And so that was kind of enough. The issue where we kind of come up, or the issue that we reach with that mindset that I had, was exactly this. We come down to here, we check the 6, and we tell ourselves, okay, well, 6 is a valid, you know, binary search tree. This in and of itself is a binary search tree. So Don't we have a binary search tree? Again, the answer is no, and we're getting thrown off by this bad boy right over here, right? This is where we're gonna get issues, okay? And we need to find a way to take into account and almost carry down with us what is going to be the maximum or minimum value that we're allowed to actually take on when we're traversing through the tree. For example, anything that happens on this side of the hemisphere is going to have to be less than 5, okay? Anything that happens on this side of the hemisphere, this side of the hemisphere is going to have to be strictly greater than 5. So we're going to need to take into account some way of basically saying, let me push a value down, like a relative value that'll say, if my root's value is either less than or greater than the minimum or greater than the maximum of what we're going to need, return false, abort mission, nobody's going home happy. That's the general idea of it. I think so the code here, I'll put it this way, the code to solve this problem is simple, but it is not easy. It's few lines of code, but again, I would argue that they're pretty unintuitive. They'll require maybe a bit of a trick that you haven't implemented before. This was my first time kind of tackling a problem like this one. So that's why I really wanted to share it, because again, I didn't find it intuitive. So I figure if one other person doesn't find it intuitive, which is probably the case, this could be at least a bit beneficial. So with these kind of conditions in mind, I hope that wasn't too kind of high level or abstract. Let's see how we can deal with this condition in the actual code. So with this one, usually I like to do my standard error checking, which is, if not root, then we're going to return, in this case, true. We'd return true because if we don't get a root, that we're valid, like we're not breaking any conditions. With this one, we're going to take a slightly different approach, and you'll see why in just a second. What I'm actually going to do is just I'll actually return the result of a helper function that I'm going to call right away, which is, maybe we'll call it validate. And with invalidate, we're going to pass the root so we can actually check, whether or not these trees and all their subtrees are BSTs. Now, if I define validate, we're definitely going to have to, right, we put self, we put root. Now, we are going to need to, like I was mentioning earlier, take into account what the relative minimum or maximum is at any given point throughout our recursive process. So I'm going to need to take some sort of value, like a lower limit and an upper limit, and that's what I'm going to call them, just so they're as descriptive as possible. And so you'll notice here that I didn't change what that limit was. So I didn't put in here like a root.val or something like that. The reason I didn't do that is because, and I implore you to actually try this on your own. If you try to put that value in there, you're going to have to kind of repeat your code depending on if you're checking the left subtree or the right subtree. And so again, when I kind of tried to do this, it got very verbose, it got messy, I wasn't getting the right answer, and I saw this trick, and it's one that I wanted to share with you. So what we're actually going to do here, before we jump into anything, is we'll set just the default lower limit of negative infinity. And the reason we're doing that is because we, at the start, at this root, we want to allow any value to go. Like, we can pick any number to be our starting root, and then depending on what side we're going down to, our lower upper limit may change, okay? If this seems a bit weird, I promise, just stick with me, and it will be clear in a couple minutes. For our upper limit, we can just set it to infinity, again, just to allow for really any integer value. Now, like in any recursive call, we need to establish what our terminal condition is. The terminal condition in this case will be, if I reach a none or a null node, then we're simply going to return true. So I'll say if not root, we want to return true. This means that we've gotten down far enough. We haven't bugged out yet, so no one's kind of yelled at me and said, oh no, like you've broken the rules, you're not a BST. We made it all the way down to the bottom, right past the leaf. And it's like, cool, all right, we're good. So we made it this far, everyone's happy. That's gonna be our terminal condition. Now, there are 3 things we're going to need to check. We're going to need to check as follows. We're gonna need to check our current value, kind of to see if it's within the limits. Okay, that's one thing we're gonna need to check. Second thing we're gonna need to check is check if our left subtree is a valid BST. And then, you guessed it, we're gonna check if our right subtree is a valid BST. If any of these return false, then we're going to jump and we're going to say, nope, game over. Otherwise, if it's like, we're good, we're eventually just going to return true, and everyone goes home and celebrates with their friends, family, and loved ones. Now, this first check should be relatively straightforward. All we're going to do is say all we're going to say is as follows. We're going to check our root.val, and we're going to compare it to our upper or lower limit. So if our value is less than or equal to the lower limit, so we're below what we're allowed to be at, or if we're above or greater than where we should be at, which is the upper limit, we're going to return false. In the first root node that we're checking, it'll never be false because presumably, we're given an integer value for this root here, and it can be whatever we want it to be. So we have open bounds at this point. They're going to close in a second, and we'll get there. But that's why we're doing this check, and as we do like a recursive step down, we'll see how that check comes into play. Maybe we'll walk through an example at the end. Now, this is where things start to get a bit more interesting. We want to check as follows. We want to check that if our left, or maybe I should say this, maybe if our left subtree is not a valid BST, return false. And we want to do the same thing here. If our right is not a valid BST, we want to return false. The way we check that is this. We'd say if not, self.validate, root.left, and we'll think about in a second like what we're going to say about our lower and upper limits, but we'll put some items in here, and then we're going to return false. If it bugs out and we realize it's not a BST. We'll do the same thing for the right subtree, but let's think about this for a second. I'm at my root node, I'm at a root node, and I want to check my left subtree. If I want to check my left subtree, I know that everything that is in the left subtree is constrained to an upper limit, to a maximum that we have. That maximum that we have is actually the value of the root, right? The maximum, we need to have a maximum, on our left subtree because all the values need to be smaller than this maximum value. There is no lower limit, okay? So the lower limit, we'll pass it as it is, which in this case is, negative infinity when we kind of start off, and our upper limit will actually be the current root value. The reason this is as follows. Let's pretend that I'm searching here. I'm looking at 514, and I'm saying, okay, 5 can be anything it wants. I now want to check if my left subtree, I want to check if my left subtree is valid or not. I need to make sure that the upper limit of this left subtree is 5, okay? That means that if we hit any root, if we hit any root that is greater than or equal to our upper limit of 5, cut it out, no bueno, return false. Make sense? And we're going to do something similar right here on the other side. We'll say if not, self.validate root.right this time. Now, since we are going to be on the right side, we know there is a minimum. Every single node on the right subtree must be at least equal to our root value. It must be at least equal to our root value. Since it can be as big as we want, there is no upper limit. It can keep getting bigger and bigger, and so we're going to push in our upper limit as the upper limit. Currently at infinity, and if you keep kind of going to the right, that's not going to change. We're going to return false if that doesn't work. And that's it in terms of the code. We'll do one quick walkthrough, but like I said, this is not a lot of code. This is not a verbose piece of code. It's not repetitive. It's pretty clean, but I'd argue not intuitive. I don't think this is easy to get on your first try. And so I'd urge you to kind of give yourself, maybe with a pen and paper, do a complete walkthrough of a larger tree if this kind of isn't biting. But let's think about this example: the 5, the 1, and the 4. Okay. So what we're going to be saying is, we're going to jump in and validate the 5, and we'll say, in our call stack, we're first going to check, is 5 within our limits? The answer is yeah. It's between negative and positive infinity. Cool. Now let's check the left subtree. Okay, and what we want to check in the left subtree is to make sure that our lower limit can be negative infinity, but our upper limit must be a 5. Since we're calling this function, we jump back in here, right? The root is valid. It's in between our bounds. It's greater than negative infinity. It's less than 5. it doesn't have a left subtree, or rather, it tries to check for a left subtree, which is none. So when we call the function, we check this condition. We say root does not exist, so returns true. We're all good on that front. Same process here on the right hand side, because one doesn't have a right child, and so we eventually return true. So it's like, cool, we're happy with the left side of this subtree. This is checked our entire left hand side. The right hand side will work out the same way. It's got a few extra steps. I see this video is already at just give or take 15, 16 minutes, so I don't want to keep dragging it on. I encourage you to jot this down and walk through it step by step if you kind of don't believe me, but I think we've got the material here to really make it clear. Now, as I realize, as always, I'm kind of blathering on without checking if this will submit, and it does. Memory usage, the memory usage will still be potentially an O of n solution because of the fact that it is recursive and we have a call stack. So on the actual call stack, when we have recursive items, that is counted toward your memory allocation. Time-wise, it's linear. We'll really tap in every single node once, so we're good. It's an O of n solution, and it's a very valid one, very efficient. And when you drop the solution in the interview, you'll get all your dream jobs. And then you can leave me a like, a subscribe, you can share it with your friends, and come back for more next time. Peace.